Hello, welcome to this video on damped harmonic motion. We're going to start by looking at a GeoGebra app. So what we've got here is modeling the motion of a particle away from a central point. And the distance of the particle away is given by x. This is actually x on what we usually think of the as the y-axis, and here's time here. So this is the differential equation. You'll recognize this as one that we've seen for simple harmonic motion. So we've got the coefficient of dx by dt is 0. So we've just got d2x by dt squared plus 4 squared. So that's 16x is equal to 0. And if we start this particle moving, we can see that we get simple harmonic motion. We just get a trig sine or cosine curve. I'm going to just pause that and make t go up to 10 so that we see the whole graph. And we've got this is a point here, but this is modeling the displacement from the center. So you can see the displacement there going to 0. So this is value of x, which is on the vertical axis, goes up positive here and negative down here. So this is our simple harmonic motion. You can think of our particle as going backwards and forwards either side of the central point. Now, let's have a look. I'm just going to bring that back there so it's not distracting. Let's have a look at what happens if we change this value of k. Value of k is the coefficient of dx by dt. So I'm going to just increase that slightly. So let's make it 0.6 will do. And you can see that now what's happening is if we start it off again, we started off again, we still get the simple harmonic motion, but it's gradually decreasing in amplitude. Let's just pause that there, bring it out here. So we get this graph. And that is called damped harmonic motion. The simple harmonic motion is being damped down until it gradually dies away. You can imagine that happening in real life if you had a pendulum that was rubbing against something, or air resistance is gradually slowing it down. And of course, this is a homogeneous second order differential equation, which we've seen that we can solve, and where we get discriminant which is negative, we get e to the power of the real part of our roots of the auxiliary equation, e to the power of that times t, times, then in brackets we had a sine of the imaginary part times t plus b cosine of that. So as we increase k here, what I'm going to do is, if you look at the discriminant is gradually decreasing. And if I increase k to 8, let's do it carefully so we don't overshoot. There we go. K equals 8. So now what we've got is we've got something which actually doesn't cross the x-axis. If I just go back a little bit, when k is just less than 8, discriminant is still negative. It's still crossing the the t-axis, I should have said. Still crossing the t-axis. So we're still getting some motion the other side of the center. So if we start somewhere away from the center, we still get some motion away from the center. When we get to k equals 8, we've now got a discriminant which is, discriminant which is equal to 0, and we now don't cross this axis, and that is called critical damping. So critical damping is when the discriminant of the auxiliary equation is equal to 0. And if you remember that that means that we would have, so we've got repeated roots of our auxiliary equation, and we then need e to the power of that root times t, but we also need, instead of just a constant times that, we have ax plus b times that e to the root times t. Once we get to a positive discriminant, gradually that gets that it's more and more damped. So it actually takes longer to get back to the center, and that is something called over damping. So that's where we would have two separate roots to our two separate real roots to our auxiliary equation, and we have a e to the minus something times t plus b e to the minus something else times t. So let's have a look at some examples, and we're going to see where one of these equations comes from, and then we'll solve those equations. I'm just going to now switch to looking at working under the visualizer. So if I just share my visualizer. So you've got a list in your course workbooks here of this is heavy damping. It's also called over damping. That's when the discriminant of our auxiliary equation is positive, and we have two distinct roots. Critical damping, which is when we've got equal roots, the discriminant is 0, and light damping or under damping is when we've got complex roots to our equation. Yeah, I think that's it for the moment. So let's have a look at how this works. So we are going to work through this question. So we've got a particle P of mass 2 kilograms moving in a horizontal straight line. At time t seconds, the displacement from a fixed point is x, and P is moving away from O with speed v. Then we've got a force of magnitude acting on P in the direction of PO, and we've also got a resistance of magnitude 16V. So I have sketched out a diagram of this. Let's see if we can see that here. Let's just get that in a place that we can see it. So we're going to work on here. Oops. So here's my point O. I've shown the distance x here, and here's my particle P. We're going to take this direction as positive. So in the situation where we see it here, we've got positive x. We've got a force of magnitude 40x acting in the direction of PO. So PO is that direction. So we've got 40x acting in that direction. We've also got a resistance of magnitude 16V. So we're going to take V to be going in this direction, because that's our positive direction, and of course acceleration is going to be going in this direction too. Our resistance so if our velocity is this direction, then a resistance is going to be acting the other direction. So we've got 16V acting this direction as well. 16V. I think that's everything we need on our diagram. So what we're going to do is we're going to say that the sum of the forces is equal to mass times acceleration. Familiar with that from mechanics. So sum of the forces is equal to ma. So in this case, what are the sum of the forces? Well, this is minus 16v because it's going in the negative direction. So minus 16v, and then we've got minus 40x is equal to mass is 2, so 2 times a. Now, of course, v is dx by dt, and a is d2x by dt squared. So we're going to change the way we've written this equation, and we're going to get a second order differential equation. So minus 16 dx by dt minus 40x is equal to 2 d2x by dt squared. So let's rewrite that as 2 dx by d2x by dt squared plus 16 dx by dt plus 40x equals 0, and divide through by 2, we've just got d2x by dt squared plus 8 dx by dt plus 20x is equal to 0. So we've done part A. We have derived the differential equation. Part B says find the value of x when t is equal to 1. Well, to find the value of x when t is equal to 1, we need to solve that differential equation. We know how to do that. It's a homogeneous second order differential equation. So let's do that. Let's say the auxiliary equation is m squared plus 8m plus 20 equals 0, and the solutions to that are m is equal to minus 4 plus or minus 2i. You can check that yourselves. I'm not going to go through that in any further detail right now. So we've now got the solutions, or the solution x is equal to e to the minus 4t a cos of 2t plus b sine of 2t. We've got some initial values. T is equal to 0, x is equal to 0, and t is equal to pi over 4, x is equal to 3e to the minus pi. So t equals 0, x equals 0 equals we're going to have e to 0 is 1, so we've got, and cos of 0 is 1, so we've got a equals 0. So we can write x is equal to e to the minus 4t b sine 2t, and t is equal to, what was it, pi over 4. X is equal to 3e the minus pi. So 3 e to the minus pi is equal to, well, if we put in pi over 4 there, we get e to the minus pi times b times sine pi over 2. Sine of pi over 2 is 1, so b is equal to 3. b is 3. So x, oops, let's just move this page a little bit higher. There we go. X is equal to 3 e to the minus 4 t sine of 2t. And now we can find the value of x when t equals 1. So t is equal to 1. X is equal to 3 e to the minus 4 times sine of 2. Be very careful, make sure that you've got your calculator in radians mode, and you can calculate that, and we get 0.049963. We should round that, and we're going to give that to 3 significant figures, so that's 0.0. I'm going to round that up to 500 to 3 significant figures. So that's our first example. Let's have a look now at the second one. Where have I got that? Here we go. So if we look at the second example, there we are, get that one out of the way. I think we can do that on this page here. Down. So we've got an end of a light elastic spring attached to a fixed point A. We don't really need to draw a diagram here because we are given the equation of motion of the spring. So we've got d2x by dt squared plus 2k dx by dt plus 2k squared x is equal to 0, and k is a positive constant. So we're going to find the general solution to the differential equation. It's going to have a number of constants in, and then we're going to find the period of oscillation. So for A, this is a little bit more algebraic. We're missing some numbers here, but we can still follow the same method. So we're going to write the auxiliary equation, which is going to be m squared plus 2k m plus 2k squared is equal to 0. We need to solve that, so let's complete the square. So that's m plus 2 squared and then from that we'll get sorry, and m plus k, that should have been, I was confusing myself there. So from this we're going to get m squared plus 2km plus k squared, so we need another plus k squared here equals 0. So m plus k squared is equal to minus k squared. So m plus k is equal to Ki. So m is equal to minus k plus or minus ki. So the general solution to the differential equation we've been given is going to be x is equal to e to the minus kt, that's coming from this real part here, times a cos of kt, that k is coming from this imaginary part here, plus b sine of kt. For part B, we need to work out the period of oscillation in terms of k. Now, the oscillation is not going to come from this exponential part, it's just going to come from the trig part, and we can write our a cos of kt plus b sine of kt in terms of in R alpha form. So that will be R cos of kt plus alpha. The time taken, the period for that to go through a full oscillation, well, we want to say that for kt has got to go through 2 pi radians, so we want t to be equal to 2 pi over k. So period is 2 pi over k, and that would normally be seconds. So that's the period of oscillation. And that's really all we have to do for this question here. So we've not addressed any different kinds of differential equations here. These are homogeneous equations, and we can do exactly what we've done before. I'm going to finish there, and we'll cover forced harmonic motion, which is a little bit more complicated, in the next video. So I'm going to leave example 3 for that one. Thanks for watching this.